going on? The day's a casual Monday. So it'll be Thanksgiving and such. There's not really a lot of class stuff going on. Got around 3 hours of homework to do. I want to do today. It would be really cool to finish this book. So yesterday I read this algorithms chapter. Right now I'm about to read this architectures of arithmetic processors chapter. Then tonight I want to finish the Gleam dependency graph, like the suggesting to unlock dependencies if we cannot find a resolving set of dependency versions because you have one locked. And any other time after that, I do laundry at some point, and then work on Punnington. So I need to get my counter back up from yesterday. It was at 32. Counter clicker. So it's at 32. So every time I say like or like filler words, I'm trying to stop doing that. So that's like the open source fund. Yeah. Shout out Lacorny Chon. So a casual issue yesterday. And no, I'm not the only contributor, so that's convenient. This is mostly the Quartz docs fork. Alright, I think I'm ready to start reading this. It's gonna be 651 plus 26. Alright. Turn my amp down tight. This chapter presents alternative architectures and algorithms for the arithmetic operations in a digital machine. So this is quite relevant. All of our, to go back to Pun Engine, all of our circuitry that is actually doing something useful, aka not networking, is, not all of it, but a lot of it is accumulating different like market indicators. In the naive example, or in the simplest example, this moving average accumulator. And it would be nice to know how to do the other things this chapter talks about being able to do. Like that was an acceptable use of like the different addition tactics, subtraction. I mean, you know what arithmetic is. So this is quite useful. Many algorithms in digital signal processing require repeated execution of arithmetic operations, so it is important that they be implemented efficiently. How these operations are implemented depends on how numbers are represented in a machine. That is true. The unsigned, even here, I was experimenting with using signed and unsigned without really understanding the difference. Excuse me. So briefly examine the common use scheme for representing positive and negative numbers and fractions. We'll examine algorithms and architectures for implementing addition, subtraction, multiplication, and division of fixed point numbers. Numbers are represented by a string of characters and a positional notation having a radix, aka base. Binary number system has two symbols and a radix of 2. N-bit unsigned binary number is represented in positional notation as a bit string. All digital machines encode numbers in a word of bits. The word has a fixed length, and the interpretation of the pattern of bits depends on the encoding format used by the machine. Do an audio check. Bit string. Is it not pulling the screen over? It appears to not be pulling the screen over. All digital. Huh. Is it not pulling the screen over? It's like frozen. Yeah, it's frozen. That's fine. Discards. Yeah, this isn't working here. We go to. So I guess I can't do that, so we just got a free ball. Video capture device, pipe wire. Make a new one. Nah, wrong one. Rip. Discard this. Remove. Yes. New. Video capture device. No, I need a. What do I need? Display capture? Display capture. Crop? No crop. Let me put the camera above it. Theoretically, that works. Alright, cool. Yeah, I guess it just bugged a bit. Maybe we should give this to OBS. Kind of been leeching off OBS a bit. Alright. So, we have these bit strings. Just make sure. The book was showing there. B10 is a. So this is a decimal number. It's formed as a weighted sum of ascending powers of 2. The most significant bit having the greatest weight. Okay, so you're looking at the weights as the multipliers of the ones or zeros in a bit string. An n-bit word can represent 2 to the n distinct numbers, but the dynamic range of numbers that are realized is dependent on the encoding format. An n-bit unsigned binary format can represent decimal numbers from 0 to 2 to the n minus 1. So, binary number can be expressed as a weighted sum of ascending and descending powers of 2. Perhaps this is in the signed case. Decimal values multiplied by the weights. So the decimal value of a number is the sum from negative n to n minus 1. So what is m and n here? N is the amount of bits in it. M. Did we define m or did we just write m? Looks like we just wrote m. So what is m? And so plus m. Yeah, so I'm not sure what m is. Or I think, is there anything too obvious saying what it is? So we're just gonna have to not understand that. The weights having a negative power of 2 form the fractional part of the number. Oh, so this is talking about floating point. Oh. So m. Oh, okay. So I think it's talking about floating point now, and m is the amount of bits representing the fractional part. Okay. But then again, these negative also represents the fractional. So maybe m is the. Oh yeah, this is showing the. It's approaching negative m. This is approaching n minus 1. So yeah, I think that's right. Yeah, I should have just kept reading and shut up. Though I'd probably move this above. The radix point for an n-bit integer is located immediately to the right of its least significant bit. The radix point of an m-bit fraction is located immediately to the left of its most significant bit. Fixed point numbers have their radix point in a specific position in a computer word. The radix point is not implemented physically in the machine. The designer must keep track of this location. The arithmetic sign of a number in a digital machine must be encoded within the bits of the word. Sign magnitude, 1s and 2's complement. 1s and 2's complement are irrelevant. In sign magnitude representation of positive and negative numbers, the most significant bit of a word is the encoded sign bit. So yeah, that's just having a literal signed magnitude at the front. So I know 1s and 2's complement. The signs of the two-sign magnetic. Am I done? Talking about magnets right now? So yeah, the dynamic range is -2 to the n minus 1 minus 1 to +2 to the n minus 1 minus 1. So the problem is you have positive and -0, I believe, in this, and you cannot just casually add. You cannot just use like the elementary addition algorithm to add them. I guess you can largely. So the problem is the 2 zeros. 1's complement. So there's 2 zeros, full 0, and full 1. Whereas in 2's complement, full 0 is 0. There's just full 1 is the min. So it's the same dynamic range, but negative numbers are different. Each positive number has a negative counterpart, including 0. And you complement the bits to get the negative counterpart. You have to handle the 2 0 representations. This is why we use 2's complement. Invert and add 1. -2n, so it kind of considers 0 positive when you're looking at the range. There's -2 n minus 1 to 2 to the n minus 1 minus 1. So the 2's complement system is important in design because subtraction of 2's complement numbers is very simple hardware realization. So yeah. So let's talk about fractions. 2's complement of a fraction is defined by b comp 2 minus b. B plus, so the inverse. 2 minus b. Where's the fraction at? Start at the least significant. So what is a fraction? How are you storing a fraction? Is there... might have to, I'm kind of thinking of this in like the Haskell rational type, where your rational is just a ratio of two integers. Perhaps that's not the case in this. And a fraction is just referring to a fixed point. I think they're talking about fixed point. Start at the least significant bit and complement all the digits to the left of the least significant one. Least significant one. The word same process used to form the two's complement of an integer. Special case is 1, that represents -1. So this is a signed fixed point. I think they all are. Since the signed bit is negative and the two's complement of 1, all zeros is 2 minus 1 equals 1. Integer plus 1 cannot be represented in the two's complement fraction system. Really? 0.1, so it's like 0.9 effectively, yeah. Yeah, that's kind of crazy. You cannot represent the number 1. Addition and subtraction are implemented in all arithmetic processors. There are several alternatives between hardware cost and performance. Give me performance, bro. The ripple carry adder presented in chapter 4 is limited by the time required to propagate a signal. I'm gonna actually shut up and just start eating. Quite a useful diagram there. Talking about a few designs for combinational multipliers. So what's inside this? Hierarchical decomposition. The method for designing a sequential binary multiplier has two main steps. Choose the data path architecture and design a state machine to control it. For a given data path architecture, the state machine must generate the appropriate sequence of control signals to direct the movement of the data to produce the desired product. So here we have a multiplier and a multiplicand. An adder. So when the multiplier is smaller than the multiplicand, sequential 8-bit. But maybe they just filled this with zeros. So perhaps these store carry of a sort. So here it is, let's explain what it does. Along with a single adder, shift registers are allocated for the multiplicand and multiplier. And a fixed register is allocated for the product. The multiplicand register is sized to the length of the product register to accumulate the shifting operations at each cycle. Okay, the controller must assert ready and then wait for an external agent to signal start. When start is asserted, the controller must deassert ready, load the registers, direct the shifting and adding of the data to form the product, and finally reassert ready. The bits of the multiplier register control the shifting and adding operations that form the accumulated product. The architecture in 1016 used only one adder and separate registers to hold multiplier, multiplicand, and product. Combination of multiplier in 1013 does not use storage registered, but it requires that the data words will be held externally until the product is formed. So this has implications. This has implications for external storage or bus utilization. In contrast, a sequential adder can release its external data paths as soon as the registers are loaded. True. Note that the long words do not require more area for logic other than that needed to properly size the registers in the adder. The controller of the sequential multiplier architecture in 1016 loads the multiplicand and multiplier words into their registers, then shifts the multiplicand to the left relative to the product register. At each step, the multiplier register is also shifted, but to the right. The value of multiplier of 0 determines whether multiplicand is added to product. There's 0. Okay, so yeah. Synchronous movement of data is depicted in 1017, so we'll have a thing to work out in a second. Addition is executed as parallel addition of the entire words. Partitioning the design into a data path and a controller gives the Verilog structural decomposition. 1018. Controller data paths are separately encapsulated Verilog modules instantiated within a TLM. M0 is the least significant bit. It controls state transitions. So that's what STG based control design. So state transition graphs. So we're shifting this left, shifting this right. An arc, okay, an arc without annotation denotes an unconditional. Here's our controller and our data path. See, I don't really care to be able to like replicate this, but it's more that when I want to be able to know what I need to look at to write good circuits that are related to this. So we have some Verilog. So this is the state transition. So it's actually not that complicated. Multiplier right shift, multiplicand left shift. If add, add. One clock cycle multiplication is kind of dope. So let's just read. I trust the waveforms. I just want to read the Verilog. So one less state here. What's with the waveforms in the middle of the Verilog, bro? So here's our state transitions. And in the data path module, word for product. So what's the difference here? So if reset, load words if shift. So multiply right shift, what would I about shift? If add shift, you're adding and shifting at once. Okay. So what is this ASMD based one? So the transition graphs were nice. They only have a few states. When there's a lot of states, there's only so many lines you can draw on a 2D surface, bro. ASMD charts. Algorithmic state machine chart and data path. ASMD charts. Facilitate scalable, portable, and reusable designs. After this section, I'm going to take a little 5-minute break. So this is a state machine, more of a state machine-ish look. So yeah. I'm not too concerned with the chart, the state machine. I'm curious as to how its implementation is more generic. So as a parameterized word length, idle, shifting, so this is just defining the states here. So we have combinational logic on these levels. Change in start, state, empty or multiplier, flush, case state. So we are changing the state. And then on the data path side, so we're contrasting the controller and the data path. And on the data path, oh, I thought that what a black dot was on my screen. So reset and flash on those words, shift and add. So, I read that. It's inefficient because, okay, so now we're going to implement the shift add one where it does both of these. Correct. So shift add. Yeah, so that's expected. I'll read the summary. Previous examples have illustrated how state transition graphs and algorithmic state machine and data path charts can be used within hardware description language. The amount of abbreviations in a sentence is impressive. State machine controlling a data path. Portable descriptions. We're going to summarize them, but not before we show you a waveform. Just randomly. Let's see partition. I do like this aspect. Partitioning the design effort into your edge-sensitive synchronous behavior, controlling your state transitions, one or more combinational behaviors, and/or continuous assignments, specifying the next state. Yeah, and then you have your edge state synchronous behavior for your data path operations that are clocked. And a level-sensitive behavioral description of the combinational logic of the controller. Initialize all output varies to 0. Yeah. No latches. I might need to do that. After this chapter, we're going to look back into my multiplier. Or sorry, into my moving average accumulator and see if there's anything obviously suspect. And I was thinking of writing a better test as well, very later. Use blocking assignments and a level-sensitive behavior describing the combinational logic for the next state. Do not mix data path operations with the next state and output logic. Write a separate synchronous behavior describing the data path operations supporting the architecture. In the behavior describing data path operations, use non-blocking assignments and condition the activity flow on the output signals generated by the data path controller. Reduced. So how much is left in this? 719. This one apparently just uses less registers. Then we have a binary multiplier. Oh, we still got to get to the dividers. Yeah, there's still a lot to go here. It's not even to dividers yet. Why is this slower than me scrolling? Yeah, we're gonna be here for a while, bro. Now we're talking about dividers. 719. Ooh. That's still like 60 pages, dude. Lame. Alright. I'm gonna put some stuff away. Put my cup up. Probably vacuum all the crumbs I just wiped on the floor. Yeah. Most we're gonna start doing laundry. I'll just put on this one. I'm gonna just leave it on this. Turn the camera off. Sekundочку. Rip. So I was just reading this. Check. Good. So it saves a lot of area, impressively. So you got that. Now let's look at these. Implicit state machines 6, 7, 8 consist of a cycle behavior with multiple embedded edge sensitive event control expression settings. So we have you recover a wasted cycle. An implicit state machine controller for the synchronous binary multiplier whose architecture was above needs to follow these requirements. Ready is to be asserted at the first active edge of the clock after reset has been cycled. Ready indicates that the multiplier is ready to respond to a start signal, with reset deasserted. Ready is to be deasserted while reset is asserted, and after ready has been asserted, it is to remain asserted until the first active edge occurs with the start asserted. The machine must begin a multiplication sequence at the first active edge of the clock at which start and ready are both asserted. Once the multiplication sequence is initiated, the machine is to assert a signal, ready, at the first active edge of the clock at which multiplier is empty. The assertion of ready is to coincide with the formation of the value of product. Ready indicates that the product can be read by an external processor. Once the multiplication sequence is initiated, start is to be ignored until ready is asserted. The data paths for word 1 and word 2 are to be ignored after their multiplicand and multiplier registers have been loaded. Seems legit. Ready is to be asserted until start is reasserted. I already said that. The machine must recover from a random assertion or reset during a multiplication sequence. The machine must operate correctly if start is asserted randomly, and if start has a duration more than one cycle of clock. See, I understand the principles. Just trying to kind of speed this up a bit. Inevitably decreasing understanding, but it's kind of worth it to me right now. It wakes up. Find here. I'm really trying to get to a division. Okay, we'll look at Booth's algorithm. Widely used. So that's a nice feature. The decimal value of a number in an n-bit 2's complement format can be gotten by multiplying the leftmost bit by negative 2 to the n minus 1. Okay, yeah, there's multiple steps to this. Multiplying the remaining bits by 2 to the I, yeah, that's good. Yeah, that's fine. The negative weight of the leftmost bit is expressed as a signed digit notation as an underscore. So negative 7 is a negative 6. Ordinarily, the bits of... Hmm. Hmm. That is a good point. It's kind of negative 8 plus the right. Never really considered it. Never really considered that. In Boots, the bits of a number can have positive and negative weights. The key to Boots' algorithm is that it skips over strings of ones in the multiplier and replaces a series of additions by one addition and one subtraction. For example, the word 4140 is equivalent to 2 to the 8 minus 1 minus 2 to the 4 minus 1. Hmm. So if you look at this thing where so the 8th bit underscore is effectively 256. So that's like negative 256. Two to the 8 minus 1. 2 to the 8 minus 1 is the max. But we don't have these 4 bits, so you can imagine inverting them. Yeah, okay. That's legit. So in order to multiply negative numbers, you can exploit this relationship to reduce the additions. So it recodes the multiplier by detecting strings of ones and replacing them. 10-1 summarizes the recording rules. The algorithm reads bits from the LSB to the MSB, and the value of 2 successive bits determines the Booth recoded multiplier bit, BRC with I. 0, 0. So you have, it's like a carry of sorts. That's kind of big brain, bruh. Bit pair encoding. Two-bit encoding representing 5 states. Bit pair encoding. I think I'm satisfied with what I understand of that currently. I'll still read the Verilog just for recall's sake. BPEP. BPEP. Bit pair encoding bits. BPEP. So this is on the state start BPEP. Clock and reset. Load words. So we store the words in the multiplicand. And the multiplier. Product. Shift. We shift. M0 del. M0 del is a reg. Starting at 0. 0 del, right shift 2. 0 del, we store that back in M0 del. Product, sub. We have some waveforms. Multiplication of signed binary numbers. To prepare for multiplication of fractions. So another tactic is negative multiplicand, positive multiplier. Or this is when you have this case, okay. Sign extend the multiplicand. Then you have the inverse case. You just extend the sign of the multiplier again. Sorry, now you sign extend the multiplier. Then you add the shifted copies of the multiplicand, but instead of adding a copy of the multiplicand, it's excision corresponding to the extended sign bit. You just add the 2's complement of the multiplicand. So now we 2's comp the multiplicand. Negative multiplicand, negative multiplier. And they're both negative, both 2's comp. Not talking on fractions. So I think I am satisfied knowing the algorithms. Not too bothered here. Multiplication of two positive fractions. So I'm fine on this. So a division. I want to understand the basic algorithms, but yeah, I don't care about the particular cases as much. So we have a subtract and shift from a quotient. Subtract the divisor from the dividend repeatedly until the remainder is detected to be smaller than a divisor. Okay. And then increment the counter. That makes sense. So what does that look like in real life? Architecture is effective but inefficient. Use more registers. Very long. Dividend. Keep subtracting the divisor. Comparing the quotient to the divisor, or we're accumulating the quotient. And then once the divisor is bigger than the dividend, we consider that the remainder. So yeah, I want to see this. Checks free divided by 0. So we sign extend the one vector. It's just a bit. Dividend, divisor, increment quotient. Sometimes the synthesis tool will not recognize economies in the architecture. Two's complement subtraction, the carry bit reveals the relative magnitude. So this implements the realization that the carry bit in 2's complement subtraction denotes the relative magnitude. Unsigned binary numbers have a particularly efficient setup. Yeah, I think I'm good on this. What's this optimization? Self-aligning divider. So that's when you have smaller divisors than dividends. Waveform, reduced register. Exploits the fact that the contents of the dividend register are shifted towards its MSB. So you just store the divisor in the quotient. You store the dividend in the quotient. And you, because you're shifting it. Okay. So I trust that. Simple method form the quotient two numbers, divide their magnitudes, and just assign a result. There is, of course, more complex algorithms. Alright. So I know I skipped some there, but I'm still satisfied with that. I think, what time is it? So I've been on here for an hour 30. Alright, I'm gonna do my laundry calculus 2200. Then I'll get back on, finish the other chapter while intermittently working on this. We'll take a look at ich-ouch protocol parsers. And yeah, so I'm just gonna end this one. But yeah, solid chapter read there.